This is going to be our second video on related rates, and we're going to take a look at our second example. So here a boat is pulled toward a dock by a rope from the bow through a ring on the dock 6 feet above the bow of the ship, or of the boat. The rope is hauled in at a rate of 2 feet per second. And our question is, how fast is the boat approaching the dock when 10 feet of rope is out? To solve this, we generally want to draw a picture. So take a moment to write this down on your sheet of paper, pause the video to do that, and then once you've done that, we can move on. Okay, so to solve this problem again, we want to draw a picture to see what's going on. So let's draw the boat here, and we have a dock. There's a rope attached to the top of the dock and the bow of the boat. Here's the water. And we have some angle theta here. We know that the dock is 6 feet up, above the bow of the boat at least. And we know that currently there is 10 feet of rope out. Let's just go ahead and call this variable A here. Now we want to know how fast is the boat approaching the dock when 10 feet of rope is out. So if this distance is A, we want to know dA dt. And then the question is, what kind of a formula can relate all of these things? Well, what else do we know? Besides this is 10 feet, we also know that this rate of change of this hypotenuse here is, so let's call that C is 10 feet and dC dt we were given, and that is 2 feet per second. So that's something else that we know. And then we need to find a formula that relates all of this information. Well, how about we just use the Pythagorean theorem? So c squared is equal to a squared plus b squared. So b here would be our 6 feet. And let's see if we can solve this problem. Well, if we derive both sides here, we get 2c dc dt. We're deriving with respect to time. And on the left, we get 2a dA, on the right, we get 2a dA dt plus 2b dB dt. All right, we know what c is, we know what dC dt is. We know what a is, or we can find it, and we are looking for dA dt. That's what we're trying to solve for. We know what b is, and we also happen to know what dB dt is. So let's go ahead and think about that. Well, first off, what is A? If our triangle here, our right triangle, has a side length of 6 and a hypotenuse of 10, then what is our other leg? Well, we can use the Pythagorean theorem to find out that A is 8. Or we can also notice that this is a 3, 4, 5 right triangle. So by multiplying all of those by 2, we get 6, 8, 10. All right, now the other question is, we need to make sure we know what dB dt is. Well, this height is never changing, so what is our rate of change there? That is 0. So now that we have all of our values here, then we can just plug them in. First off, we notice these 2's cancel, and then let's go ahead and plug everything else in. C is 10, dC dt is 2. A is 8, dA dt is what we're solving for, plus B, which is 6, times dB dt, which is 0. Well, this goes to 0. We get 20 is equal to 8 times dA dt, and I just realized I made a mistake. So let's go ahead and take a look at what that is. We said earlier that the rope is hauled in at a rate of 2 feet per second. So this dc dt is actually negative 2 feet per second. So this value right here should have been a negative 2 when I plug that in. Why is that? That is because the length of this rope here is decreasing, right? We're hauling in the rope, so this is decreasing along the way. So that value should have been negative. So that is negative 20 is equal to 8 times dA dt. So we divide by 8 and we end up with negative 5 halves is equal to dA dt. In other words, the rate of change at this instant is, of the horizontal distance between the bow of the boat and the dock, is negative 2.5 feet. As in, the boat is approaching the dock at 2.5 feet per second at this instant when the rope has length 10 feet. All right. So we solved that first problem. We got a similar problem with that on that same type of question here, or the same scenario. And that is, part B is going to ask, at what rate is the angle theta changing at this instant? So again, we have our triangle. We had this was 6 feet, this was 10, here was our theta. And we want to know what our rate of change of theta is. So we need something that relates theta with the hypotenuse and some of the other information we're given. Or technically, since we've calculated the first part, we can relate this to the opposite side if we'd wish as well, since we know what the rate of change of the opposite side is as well. But since we had to calculate that, and sometimes in calculations we might have a rounding error, we didn't in this case, but sometimes we might, it's usually better to try to solve this from our original information if we can. And in fact, in this case, we can. So let's go ahead and do it that way. So if we want to relate our information that we have and this angle theta, we can note that cosine of theta, so the formula that does that is cosine of theta is equal to 6 over c. 6 is a constant here. C, even though we know it's 10 at this instant, this c is actually changing. Right? In this situation, this c value is changing because we know dc dt is negative 2 feet per second. The 6 is not changing, so that's a constant. So I can leave that as a constant. I need to put c as a variable, though, since that is changing. And of course, theta needs to be a variable here because that is changing as well. And in fact, dc dt is what we want to calculate. Now, we could take the derivative with respect to time as is, or I could rewrite this to c times cosine of theta is equal to 6, and now take our derivative with respect to time. And so let's do that. Well, this right here, we take the derivative. This is a function with respect to time, and this is a function with respect to time. So to take our derivative, we do the product rule. So the product rule on the left says we take the first times the derivative of the second. All right, what's the derivative of cosine? That is negative sine of theta. And then chain rule says to then derive the inside function with respect to time. So that is times, and multiply by that. And so that is times d theta dt plus, all right, now we need the derivative of the first, that is dc dt, times the second, that is cosine of theta, is equal to, and what is the derivative of 6? 6 is a constant, so that is 0. All right, now we need to plug everything in. We were told that we're finding this change in the angle when c was 10, right? Because it says at this instant, and that is referring to our earlier scenario when t was 10, or sorry, when the c was 10. Now the question is, what is sine of theta? Recall that at this instant, this adjacent side is 6, the opposite side is 8, and the hypotenuse is 10. So sine of theta at this instant is 8 over 10, or in other words, 4/5. So we get negative 4/5 here because it's negative sine of theta. Times d theta dt. D theta dt is what we're solving for, so we don't know that yet. That's what we're trying to find. Plus dc dt, well, that was negative 2. Times cosine of theta. Cosine of theta, if we look at this, is 6 over 10, so that is 3/5, is equal to 0. So here we get 10 over 5 is 2, that is negative 8, times d theta dt is equal to 6/5. Divide by negative 8, and we end up with d theta dt, negative 8, this is 6 over 40, which reduces to negative 3 over 20. Oh, sorry. That is negative 3 over 20 radians per second. And we are done.